Okay, hello. Yeah, my name is Markus-Berger. I'm a postdoc researcher at the University of Rostock, and my co-authors are Joern Ploennings and Martin Wogan, who's also in the audience there. And the title is Input Strategies for Precise CAD Modeling with Modern Interaction Devices. So this is not a system, but this is more of a review and a conceptual paper in which I take a look at the current state of the technology and state of the art to see well, what we can do with modern interaction devices in the construction sector. And this is also generally part of what I'm researching in terms of multimodal display and interaction systems in this sector. So the fact of the matter is we have more specialized interaction devices than ever before. We have VR glasses with the wand-like controllers added to them, like the MetaQuest Pro here. Now coming out the Apple Vision Pro with more of an indirect gesture control system and no dedicated controller yet. There's very dedicated controllers like force feedback haptic gloves or haptic devices that are currently mostly used in applications like surgery training, but that would have obvious benefits for some CAD modeling tasks. So the question is, especially if you look at these two VR mixed reality headsets, they both have Pro in the name. So the question is, if they're so pro, then why are we not using them in professional contexts? What's the issue here? Why is mouse and keyboard still dominant in CAD modeling tasks? So yeah, the questions I'm asking: why are we still mouse and keyboard? What else could we use compared to mouse and keyboard? Just like what is possible? And then of course the obvious question: what should we use? Of those options that we have. And so from these basic questions, I want to construct some research questions that I then go through in a literature review. So for the answer for the first one, or like the obvious answer for why are mouse and keyboard still dominant for CAD input, is well, it's cheap, it's available, we know how to use it, and it's multifunctional. And I think the first three are probably downstream from the fourth one, because yeah, we use it because it's so multifunctional, because it can do so many things. Like it proved very useful for a lot of different tasks. Like we can type away on the keyboard, we can click on things. It just works well, and we're all used to it. So the question then is, okay, so it can cover all these things apparently we need to do. So let's classify what are the things that we need to do while we are CAD modeling. Let's start there, so that we have a basis of comparison for other devices to see what they can do and what they can't do. Then, for the second question, what else can we use? Obviously, there are many device classes that we have, and they can be used for some tasks, and maybe even better at specific tasks. And there's some literature about this, like Fiorentino et al., where they compare haptic devices to mouse and keyboard control. So the question here is, which parameters can we use to figure out if a device is actually useful for CAD, and what specific aspects of CAD interactions they are useful for? So basically classify the devices, classify the tasks, and then see what device can we apply to what tasks. And the third question, what should we use? We should, of course, use the most effective combination of devices or the most effective device. And so the question is, how can we evaluate the performance of these devices? What are the metrics that we can use to compare them? So this is sort of an attempt at systemizing this problem and looking at the literature to figure out what do we currently know. For the first question, what are the functions that we need while we are CAD modeling? And there's some literature on this, also Fiorentino et al., which I noted earlier. And in that case, they split CAD modeling into selection, manipulation, navigation, and like system control tasks. I renamed them slightly, but this is the gist of it. But I think what is missing there is that there's two kinds of manipulation. There's the spatial manipulation, where we just place objects, points, lines, whatever, into space. And then there's a whole different class of problem where we have numerical inputs, where we actually make sure that they are where we want them. Like that we can place a line anywhere and it's probably going to look right, but this line often has to have a specific length, it has to have a specific endpoint, a specific starting point. It's related to topology, to to specific regulations even in some cases. So this is the kind of the extended version of the classification from Fiorentino et al. And I put some examples into each of those categories here. So if we are spatially manipulating, we might be positioning something, we might be rotating something, we might be scaling something. And there's more sometimes, but those are the biggest tasks we actually need to cover. So this is the answer for the first question. What are our functions? Second questions, what are the parameters that describe a device? So what a device can do. And here this is something that's not based on anything that's previously in the literature. This is sort of a thing that I think classifies this well, that covers the space well. So there's three aspects, I think, that are important with the device. There's the spatial reference, which I made some nice pictures for. So we have the spatial reference, which basically covers how do we select a location on the object. Like we have objects that we are modeling. How do we select a point? How do we select a line? Any specific point. So, and this can either happen directly on the object. For example, if we just put our finger on it, I just say this corner right here. Or do we have something where we have a projected sort of surface? So am I maybe standing over here, and I'm pointing here somewhere, here on the object, and through some projection, the system knows I'm going for this corner. So this is one big difference in devices. Then we have the input reference. This is related, but not the same thing. So basically, the issue is it translated? For example, if we have a 2D drawing board, like if we, as often used for when artists draw on computers, like I'm forgetting the name, like Wattpads, where you basically have a surface that you draw on, and this surface doesn't really have an immediate relation to the surface, to the display surface. So you're drawing on an external surface, and then there's another surface that is the display. And this can also extend to 3D displays and VR goggles. Or are we directly operating on a display, like in a touchscreen display? Are we drawing on a tablet directly? Then it's an immediate reference. Same thing in VR. If we are operating directly with one controllers in 3D space, it's also an immediate reference. And then the input progression for numerical inputs. So the big distinction for numerical inputs is, are we directly putting in the number, like we would on a keyboard, or are we getting closer to the number through some interaction? Like if you think about maybe we're twisting a knob or using a slider to get closer to a number and then kind of find our way there continuously, instead of just immediately being on the number. Okay, so this is question 2. So we have some categorizations. Now we have to see what we do with them. So I had to define some metrics, and there were some metrics in the literature already. So yeah, metrics for these interaction devices. I'm going to go through this relatively quickly. If you are interested in the details, then of course have a look at the paper. So some very established metrics from human-computer interaction are the precision and what I call the capability, often called throughput, that just define how good is a device at getting information into a system. Like human motion to information in the system. These are very quantitative measures that you can define. I added a third one for my effectiveness measures, which is the explorability. Because often we don't know what we are going to model. We are finding it out while we are modeling. So how good is a device at actually getting closer to a solution step by step? And then we have secondary measures that are more about the context of something. Do we have both hands? Do we have only one hand that we can use? Does the device have to be portable? Are we in a collaborative setting? So contextual metrics like that. And based on all of this, I made an evaluation in the form of a table, which I can't go into detail too much on now. As you see, this is sort of a truncated version from the paper. But basically, on here you see all the types of input devices we distinguished in the paper. At least it's a selection of them. There's a couple more. And then there is the contextual metrics, then our classes here, and the primary metrics are here, here, and here. And you see, for example, just to pick out an example, so what makes, for example, a 2D mouse so good? It's just very spatially precise. It has good throughput, good capabilities, and it is explorable. We can just move stuff around on the display, and there is no issue. And then we add the keyboard to that, and the keyboard, of course, is very good at numerical inputs. And we can do the same thing for a lot of these VR, like devices that we like to use in VR, and even devices that we don't see very often, like sliders, knobs, triggers, buttons. For example, if we were using a controller, or maybe even like a sort of MIDI controller, if anyone knows what that is, like basically just a board that you usually use for like controlling music interfaces. Why not use those for CAD? So there's some measures for those too. Basically, I try to collect every interaction device class we could possibly want to use. Right, and then in the paper I go on to some use cases, 3 specific use cases. The first one is a single person sitting in front of a 3D display, like an autostereoscopic display, where you're basically operating on a sort of hologram. Then the classic like VR, like one person in VR use case, head-mounted display on, controllers in hand. And then scenario 3 is sort of tailored for the Apple Vision Pro, where you're just sitting, you're using indirect gestures with other people in the room, and you're operating on one model that is probably floating in the room somewhere. And I just want to jump into one specific scenario to kind of make clear what I'm doing, which is the second one, with a slight modification that, let's just say we are in a scenario where we want to do CAD modeling while seated with VR goggles. Because often we are, when we hear VR, we are thinking about like room scale, jumping around, moving objects around. The problem, of course, is this Minority Report sort of interaction is very uncomfortable after a while. You get sweaty, your arms grow tired. It hasn't really worked out well. So let's say we're seated and we're trying to be as comfortable as possible. And why should we do this? I mean, we often draw at multiple scales, and the good thing is if we are in a fully virtual environment, we always keep the spatial context. Like we can always, if we're modeling something very detailed, we can always take a look around and see what context are we modeling and what do we maybe need to take into account. And so we can go through the table, and basically the thing here is we are occluding the real world. So this is kind of where keyboards and mouse fail, because there's issues with using it if you can see it, even if you're very good at typing. So you really want to see the device, but the space is entirely virtual. So what do we have to do? We have to give the device an avatar, basically, in the virtual world. And in the table, that would mean it needs an immediate input reference and a direct spatial reference, or it needs to be no device at all. It needs to be some sort of hand tracking, gaze tracking, something like that. And I'm kind of running out of time, so I'm just going to skip this quickly. So there's some devices from the table, basically, that are candidates. And then you can see, okay, what can they cover? You can just like mark them off. This one can be covered, this one can be covered, this one can be covered. And what do we discover? The problem is we don't have anything that can do high precision numerical input and has high comfort. And this is a very basic issue of this whole space that is correctly identified from just going through this table. And then we can look for solutions. We could have simple solutions like, maybe for this we don't care about the highest numerical precision, or we relax some other requirements a bit. Maybe we create a very specific input device, then we're back in human-computer interaction research. Maybe we could manufacture VR controllers with a high-precision knob on them where we can basically twist it to move numbers up and down in a very precise way. Just one idea. And yeah, So I'm just going to, yeah, the outlook is basically, we could do more, software could do more, we just need to figure out what actually works, maybe break some habits, and there's big advantages we could have. There's the capability of drawing more complex, like organic shapes, especially now that we're going into 3D printing in the construction sector. We could integrate AI into tools, but yeah, I'm going to stop. Thank you.